research here. Edith Cohen will tell us about monotone estimation framework and applications for scalable analytics of large data.
Thank you. So this is mostly work I did 2 years ago, but there are still some open questions, and so I would like it exposed more. I think there were lots of applications that came up. Okay, so I'll first give you the definition. It's a very simple, clean definition of monotone estimation schemes and monotone sampling schemes, and I'll talk a little bit about applications and the remaining problems. So what is a monotone sampling scheme? So, okay, so you can think, you have a data domain. It's all the possible things your data can be, okay? Think of it as a subset of vectors in RD. And then the randomization is all captured by this U value, a random seed value that is, say, it's uniform between 0 and 1. And then you can think of the sampling scheme as a function that looks at the data itself, look at the randomization, and returns something. S of V and U, it's a function of the data and the randomization, okay? Okay, and here we'll assume, and it's a very important assumption, that when we see the outcome, the sample kind of, we have the randomization with it, okay? It gives us a lot of extra power. So we can also think of S of VU as basically the set of all data vectors, because this is like a lossy thing, kind of. So from here, we can think of as the set of all data vectors that would have resulted in the same outcome with a seed U, okay? Okay.
The outcome is SVU, I'm not sure.
Yeah. So SVU is
the set of data.
Yeah, so you can, I mean, it's kind of, you can think of it both ways, right? It's the outcome, but then it specifies also some subset of the data domain. It just, yeah, that is all the possible vectors that would have given the same outcome, given you. Because it's like the information you have, okay, in some sense, okay? It's overloaded definition.
You see S of UV, and you're trying to figure out what V is? Or?
Yeah, so you try to, yeah, exactly. So that's the thing. Okay. Okay, so why? So the constraint is that I want the scheme to be monotone, meaning the smaller U is, the closest it is to 0, I can have only more information, okay? So SVU, if you would give you more information about V, like, but monotonically so, when U is smaller. Okay? So it's good that this confused definition is clear, okay? So, okay, so this is the clean scheme, okay? Okay. So you can think of U as kind of the resolution of your instrument. So the smaller it is, the more you know, okay? So what can you do with that? Okay, so now suppose I have some non-negative function over the possible data values, which is F, okay? And actually I'm interested to know what is F of V. Okay, but all I have is the information that I can get from the sample. Okay. Okay. So useful properties that I want from the estimator are the following. Okay. I want it to be unbiased, meaning that if randomized over U, the estimate would be, the expectation of the estimate would be F of V. Okay? Intuitively, why do I want that? Because actually in all applications, I would want to estimate a big sum of such problems, okay? Not just one. And then if I get unbiasedness, it will, it's better. The variance will eventually disappear, and I'll still be unbiased, okay? If there is a bias, it will stay, okay? I want the estimate to be non-negative because F is non-negative, and that way the estimate is from the same domain, which is also important. And also, another requirement is that I want it to be optimal. I want to do the best thing I can with the data, okay? So there is the notion of a Pareto optimality, which is called admissibility, which means among all unbiased and non-negative estimators, so you can get a better unbiased non-negative estimator and improve everywhere, okay? Any other estimator that has a smaller variance on one data point, if the data is V, would have a larger variance on another data point, okay? So these are three things that I want to get out of these estimators, okay? This just means that I kind of use my information the best way possible in terms of variance, okay? Okay. So how does it look like, actually? So, okay, so this is what the information I can have on f of v given u, okay? So the real data vector is v, and I'm interested in f of v, but what I know depends on u, okay? Like if the resolution is very high, there are many, many vectors that would have the same outcome. And when u is smaller, there would be fewer. So I would know more about f of v. Okay, so there is an upper bound and a lower bound that I can get, inherent. And then when you get smaller, the upper bound would go higher, and the upper bound would go lower, and the lower bound would go higher, okay? So this is how things look. So if u is here, I know the real value. Looking at the outcome, I know the real value of f is in between these two values, okay, of f of v. I don't know v, but I know that f of v is in between these two values, okay? That's the information I can get. So we can kind of think about what would be needed of this estimation scheme that I can get these properties. For example, if it has to go to fv as u decreases, because otherwise there's no way I can get an unbiased estimator if it doesn't have that property. And then intuitively, if it goes too slow, maybe I won't be able to bound the variance, okay? Okay, so this is the information I have on f of v when the randomization is u. Okay, oh, my. Okay. So this is what I want. So I'll just kind of give some preview of the results, and then I'll talk about some applications that will that motivated why I started looking at these things. Okay, so what we get is explicit expressions for estimators for any such problem for which such estimators exist, okay? So we want unbiasedness, non-negativity, we want bounded variance, and we want admissibility, okay? So it's Pareto optimality. The solution is not unique, but we can get some estimators with natural properties. One that is very interesting is monotonicity, which meaning that the estimate is non-increasing with u, okay? And then we also get uniqueness. And another interesting thing would be some notion of competitiveness of estimators, okay? Okay, so some applications, why I started looking at these things. Okay, so what does it gives us? It gives us what sampling gives us, which is a scalable computation of approximate statistics and queries over large data sets, okay? So the data is sampled very efficiently, and then the sample is used to estimate the statistic or queries that are expressed as sum of multiple maps, okay? So here are some applications. So you can think of the data as key value pairs. but multiple sets of such values for each key, like correspond to different days or different sets of observations and so on. And then if we take coordinated samples of these sets, we get a map for each key. And then to estimate statistics that are sums, we just get a sum of maps, okay? Another application that this was very useful is the sketching graph-based influence and similarity functions. So each and the more generalized coverage functions. So basically, you have kind of sets. If you can think of them as nodes and what they can cover. You sketch whatever each node sees. And then to see the coverage, the total coverage, the total influence of some seed sets of nodes, you take a sum of maps over everything that can be covered, okay? So we will focus today on this application, on the plain application, to just general statistics, okay? So think about the following. So this is some social or communication type data. So you have keys. Here the keys are pairs of, say, users. And you have some activity value associated with each key. So you have the key x, and v of x is the activity, which is non-negative, okay? For example, the number of messages going between them, the communication between them, okay, and so on. So what we will do is take a weighted sample of the keys according to these values. And there are many ways to do it, okay? And so we only get some small fraction of the keys in the sample. The way to get a weighted sample, there are many ways to get weighted samples. A common way is a probability proportional to size, which can be equivalently represented this way, okay? So suppose there is some threshold tau, and a key is in the sample if its value is larger than tau over the randomization, okay? That's how you get a probability proportional to size. So you can get a bottom k priority type, order type samples, and then tau is set dynamically, like according to a fixed, so that the sample size is fixed, but it has the same form. So you can get a lot of sampling schemes that have this. But basically, when you see the sample, you know the threshold value that was used, and you know U, okay? So you see, so when something is in the sample, you see its value. But even if it's not in the sample, because you know the threshold that we use, and you know the randomization that would have been used for this key, you also have some information, okay? Okay. So now there are samples of multiple days because the values are different across days, okay? So this is the Monday and the sample for Monday that we've seen, and then another data set for Tuesday, another one for Wednesday, and you don't have space to keep all that, so you just keep the samples. And it's much more effective for what we want to do if you coordinate the samples, which meaning you use the same set of randomization, the same UX for the same key across different days, okay? Okay, so you can think of the whole this data set like that. So here are all the different keys, all the different pairs. And these are all the different days, and these are the activity values, okay? And okay, so what do you want to do with that? You want to estimate all sorts of statistics over this matrix, okay? So you want to specify a segment of the keys. For example, all the keys where one user is in California and the other is in New York. or all the keys where one user has an Apple device and the other has an Android device, or something like that. And then you want to compute some statistics over that segment that have this form. It's the sum over keys of some function of the sets of values over different days. So there can be one or two or few different values, any subset of the days of this function, okay? So an example of questions that have this form is the total communication of that segment of keys on Wednesday, okay? And then it looks like that. Or another natural thing that you want to do is some distance, LP distance, or weighted Jacquard distance, or whatever, of the change of activity of that segment between 2 different days, between Friday and Saturday, and this is how the aggregate looks like, okay? It's the sum over all the keys in the segment of the value of Friday and the value on Saturday to the power of P, okay? Or this is another one, just look at the increase or decrease, but you can do anything, okay? Average, sum of median, max, top 3, any concave aggregate or any other function, okay? So suppose we have these samples, and then we have the function f, and we want to get the best estimate we can for that f, okay? Okay, so let's see some example with PPS sampling. Suppose all the keys and all the instances of the same threshold, but it doesn't have to be. So you draw the same randomization for each key, okay? So, and then you sample if the value divided by u is larger than tau, okay? So you get this key sampled. Okay, and then you have to work with that, okay? Okay, so now how do we do the estimation? We do it one key at a time. We look at key by key, and then we sum the estimates, okay? Okay. So this is okay, so for LP distance, we just basically sum this function over keys. And basically, we apply an estimator, okay? So we apply an estimator to the sample of that we have from that key. So for most keys, we have no sample at all. So this would be 0. But for some keys, we have some information, and we will use that, okay? Okay. So let's start with the simplest statistic, with the total communication of a segment on Monday, okay? So what we want here, we want the sum of, say, even the v values of all the keys in that segment, okay? So here there is a very simple estimator we can use, classic estimator called the Horvitz-Thompson estimator. So we look at all the sampled entries in that day that belong to where the key belongs to our segment. And then we look at the value, the value of the entry, and we divided it by the probability that it's sampled. And this would give us an estimator that is unbiased, okay? So we can get that probability because we know the threshold and we know the randomization, okay, once something is in the key, okay? So, okay. So here, suppose we want to know the sum over all the green entries. The green entries are all the keys that fall in our segment on Wednesday. But we only have, so we only look at what is sampled, which is these 2 entries. And then we take the sum of the estimate we get from that, okay? Here we have zeros, so we don't explicitly look at them. So the exact value is that. And the Horvitz-Thompson estimate is 0 for keys that are not in the sample, but it's V over P for keys that are in the sample. And this is proportional to size, so we get this estimate, okay? So, okay. So that's what we do if we sum over, if we want to estimate something like the total communication of that segment in a day. But now, okay, and then and here we actually have all the properties that we wanted. The estimate is unbiased. And it's non-negative because we divide the value that we see by p, and if that was f of v or v were positive, it stays positive. The variance is bounded, it's easy to see. It's monotone because for each key we can only get two values. We can get 0 if it's not in the sample, and we can get its value divided by p if it is in the sample, so it's monotone. The more information we have, the estimate increases. It's also optimal in the sense that it uses the information in that sample the best way possible per key. It's the unique minimum variance unbiased non-negative estimator, okay? Okay, so it works very well for f's that are on a single entry. So what about, okay, but we talked about other functions that we want to do. For example, we want to do distances. Okay, so what do we do? How do we get an estimate from these samples? Okay, so we can try to apply here the Horvitz-Thompson estimator. So for that, we will need to only look at keys. So suppose we have 2 days, Monday and Wednesday. So we have to look at keys where it's sampled both in Monday and and on Wednesdays. But these samples are taken separately, so we can't. So some keys would have only Monday, and some keys would only have Wednesday. Okay. And because we have to take a weighted sample, there's no way to have the same keys, okay, consistently without creating a huge bias, okay? Well, not a huge bias, but a huge variance, okay? So we can, okay, so now we have a sample that includes some information from some days on some keys and some information on another day from another keys. Okay, so here we have a problem because this function can be positive when one of these values is 0. So there are things that contribute to the aggregate we're interested in, to the statistics, that that don't both appear in the sample. So we cannot get an unbiased estimate if we insist on using Horvitz-Thompson here, okay? Because the 0 entries will not be presented. So if we just want to look at keys where we know both entries and take the difference and apply Horvitz-Thompson, it won't work. Okay, it will be biased. Okay. So even if it would have worked, for example, even if I was guaranteed that V is positive, all entries are positive, and therefore has a positive probability to be sampled, this estimator will not be optimal because intuitively there is a lot of information that it won't use, like. If there are keys that I know appear only on Wednesday and appear only on Monday, because I know the randomization, I can still have some information on that difference. But I won't know it exactly, but I would know something about it that I could use. I would know it's not 0. And I want to use that information in the best possible way. Okay? So here is the example. So suppose we want to do the difference over the green segment between Wednesday and Thursday. So we want to estimate, basically that's the quantity we want to estimate, okay? But we only have the sample. So we do the estimate key by key. So let's look at that key, A to Z, okay? So here in this example, we see only one value, 24. So let's look at what happens here. So f that we want to estimate is this value, which is 81. It's 24 minus 15 squared. But each time we draw the sample, we'll see something else, and we want an unbiased estimator. So let's look at the lower bound kind of we have on fv as a function of the seed u, okay? Of course, we don't have this information, but this is just what happens. We don't have it when we apply the estimator. So first, so if u is large, we will know nothing. The value could be 0, okay? But then when you get small enough, I would see the largest of the new entries here, which is 24. And when it's really small, I would know both entries, okay? So when I see the larger one, I still know that the smaller one is smaller than something. Like, so I still have some information here, okay? And then so I know something, and I want to use that information, okay? Okay. So when I actually draw the sample, I know u. And basically, if I know what happens here, like I see one of the entries, I know what I would have seen for larger u. And that information I can use in my estimator. Okay? So this is a monotone estimation problem. Okay. Because the smaller u is, the more we know. Okay? So it's monotone. And I want an estimator with these properties. Okay? Okay. So what is really happening here? So there are many, it's not unique, there are many admissible estimators, even if I try to do the best thing. So let's look at, so suppose I'm determining the value of the estimators, suppose I already know what I've done for all the values larger than u, okay? And let's see what I do with the information I have right now, okay? So here there are like supposedly 3 vectors, v, z, and w, that are consistent with my sample, and I know u, okay? So for larger u, there would have been more vectors. So, okay. So suppose I am here, and I know already all the estimates I would have returned for larger u. So what I can do here, so if I want to optimize for the vector v, I would give an estimate in this direction, okay? To estimate the variance, minimize the variance. If I want to optimize for w, I would give that estimate. If I want to optimize, and so on, okay? So I have to make sure that the estimate stays non-negative, no matter what the vector is. So I can't go too high, but then I have some freedom of choice here, okay? Okay, so what can I do? So the estimator is not unique. So I can look at some order of the data domain and optimize the estimator by that order, okay? A very natural estimator, which have the most applications, is what I call the L-star estimator, because it's monotone. It always makes the most conservative estimate it can, okay? So it makes sure that for, and it's order optimal, like it always goes for the smallest possible value of the function of consistent vectors, okay? And it has another nice property that I'll talk about now. And then there is another estimator that optimizes to the opposite. It always optimizes to the largest possible value, okay? So, okay. And they have different properties which are useful in different applications, okay? Okay, so I said this L estimator, which I'll intuitively show what it does soon, but basically it kind of optimizes here to the lowest possible vector that is consistent with your sample. Okay. So this is another definition of variance competitiveness, okay? So we talked about optimality. But then in this framework, you can always optimize for any particular data vector, okay? So under the constraints that the estimate is non-negative and unbiased to everybody else, you can try to do the best you can for this data vector. So, okay. Okay. And we defined that's joint work with Kaplan, Chaim Kaplan. We defined the competitiveness of the estimator as how far it is in the worst case over all possible data vectors from that optimal you could do for that vector, okay? So you can look at the expectation of the square of the estimate for any possible vector, for overall vectors, and you can compare it to the best you could do for that vector. And the nice, okay, so the nice property for this L-star estimator is that it guarantees you a ratio of 4. And this is tight for that estimator, meaning that on some functions the ratio will be 4, okay? Okay. So what does the optimal estimate look like for a certain data vector? So suppose this is the lower bound function, meaning it's the lowest value f could be given the information we have when the real data is v, okay? So we have the real data v, we have u, we only see s, and this is the lower bound we have on f given the value that we see of u. And to obtain that optimal estimate, we look at the lower hull of that function. And then the estimator kind of follows it, okay? You can't go above it because then you will be non-negative to some other vector. So basically, to really be optimal for that, for v, you just want to return f of v all the time. But because you're restricted to be unbiased and non-negative, when you see S, there could be other possible vectors there. That limits you, okay? So this is the best you could do for V under these limitations, okay? And the definition of competitiveness is with respect to that. Okay. So now what does the L estimator does? Okay, so this is the lower bound that we have. Suppose so. Let's look at a particular value v and what happens for that particular vector v and what happens. Actually, let's look at just the lower bound function and what estimate we return. Okay, so suppose we are here and that's the lower bound. So if that's the lower bound, it means that there are vectors that are consistent with our outcome, that this would be the value. So we just return an estimate that is this gradient here, okay? Because if we go above it, we won't be monotone anymore. The L-star estimator is monotone, meaning that to stay unbiased, we'll have to actually lower the estimate later. And and then when we see a sample and U, we know we have information of what happens in this range. So we know all the estimates we would have returned if U was larger. So that allows us to make the right choice here. We know the cumulative of what is here, and then we can do the best estimate we can under the constraint of monotonicity. Okay? So the estimate, כמה זמן? Okay. So this is how the estimator looks as a function of the lower bound function. Okay? Okay, so these are the examples for L1 distance of, okay, maybe I'll skip that. Okay, so summary of what we've seen. We define these monotone estimation schemes that are motivated by coordinated sampling, but they have other applications. So like for sketching the coverage functions or generalized coverage functions, you also can get the best possible estimators out of your sample for, and so on. We study the range of Pareto optimal estimators. The L-star estimators has particularly appealing properties because it's the unique monotone estimator. It strictly dominates the Horvitz-Thompson estimator, and it's optimal, right? And we talked about order optimal estimators. There's more in the papers about that you can optimize for a certain order on the vectors. So I use that scheme in multiple works. And I've seen actually a lot of papers that try to do this, but without optimal estimators in all sorts of contexts, because even like estimating union from in-hash sketches is a very special case of that. Or estimating, okay. Okay, let's see. Future. So I said that the L estimator is for competitive, for variance competitive, meaning that, and that's tight, meaning there are examples of function f that you can't do better than that. So I played with it a little bit, and I found an estimator that is slightly better than that. And I found some lower bounds over all estimator of that you can't do better than 1.44. But it's just a question if there is another estimator that has a overall better ratio guarantee than 4. Okay? Another question is the instance optimal competitiveness. Give an efficient construction of estimator for any map. Suppose you want the best for particular f to minimize to get the best competitiveness, okay? So the L estimator guarantees you 4 for any f, okay? But for a particular f, you can maybe do better than that, and how to construct an estimator that actually gets at the minimum possible, the best competitiveness, if that's what you want to optimize. Another open thing is that this is kind of the one-dimensional version of the problem, meaning that we use the same U, and everything is perfectly coordinated. But then with independent samples, you have different U's for different instances, and you can still think about what's the optimal thing you can do for independent samples. So with Kaplan, some years ago, we looked at that for very specific problems. But it gets much more complicated, even with 2 instances. But I think there is a lot more to do there. So I use that estimators in more applied work to look at estimating at samples from which we can estimate L1 and L2 LP differences, okay? So these are just some experimental results. So if you use independent samples, you get much larger errors. This is a particular data set, okay? And the L and U estimators with coordinated samples get you much, much smaller error. So now there are other methods to estimate differences from kind of sketches of vectors. For example, using JL-type linear projections. But projections, and then you can estimate from this lower dimensional thing kind of distances between the vectors. That's for L2. But this is a much more general scheme. It allows you to do segment queries easily from the sample. It allows you to do like the one-sided, like just look at the increase or the decrease, and a wider family of functions. Okay. So this is similar experiments for the L2 different distance. Okay. Thanks.
I have 1 or 2 questions.
Yeah.
Okay, so let's thank Edith again.